it's a pleasure to have an opportunity to do an oral presentation here. Before I begin, let me tell you a little about myself. My name is Chen Yifan, a senior from Shandong University. I major in electronical engineering. To be more specific, it's about interconnection network of global energy. My purpose today is to give a detailed description of my essay about the research on active equalization topology based on the multi-input transformer. My talk will be in 4 parts, and here is the outline. Begin with, I will be talking about the energy development tendency and the challenge that we are facing. And after that, I will explain how the development of energy storage technology can help the renewable resources. And then I will talk about the classification and the summary of battery equalization topology. And finally, we will take a look at the simulation and the mechanism analysis of transformer equalization topology. Now let's move to the first part, which is about the energy development tendency. At present, the global low-carbon process continues to accelerate. Industrialized countries have all put forward the goal of achieving carbon peak and carbon neutrality by 2050. That can be seen from the chart, which shows the changes in electricity generation in 2020 and 2021. In addition to the decrease in solar photovoltaic power generation, other energies such as wind, biomass, hydropower, nuclear power, and coal increased. Thus, traditional fossil energy like petroleum, natural gas, coal still occupies the dominant position, posing a huge challenge to the realization of double carbon target. It can be seen from the chart that, unlike other countries, coal consumption in China continued to rise by a far greater extent than any in other countries, from 669 million tons in 2000 to 21.5 million tons in 2021, and this figure will continue to grow. The carbon emissions generated by coal consumptions have also reached the peak. Therefore, promoting the development of renewable energy is currently an extremely important action. The energy situation is still grim, and the energy revolution is extremely urgent. Thus, it brings us a new question. What should we do with the crisis? And that's what we are going to talk about in the second part, the energy storage technology. Yes, energy storage technology is a key technology in the development of smart grid, energy internet, and new energy, and that can help to solve the question mentioned above to some extent. One of the energy storage technology is the electrochemical storage. Because of its advantages of early technology formation and the low material cost, is currently the most mature energy storage technology. Lithium-ion, yes, in like the picture, lithium-ion battery has high energy density and high average output voltage. Self-discharge of a good battery is small, below 200% per month. The range of operating temperature is 20 degrees under zero to 6 centigrade. With its excellent cycle performance, fast charging and discharging, the charging efficiency can up to about 100%, and the output power is really high, making it long-lasting. It does not contain toxic and hazardous substances and is called a green battery, but there are still certain difficulties in its application in distributed generation. However, because the voltage or capacity of the single battery cannot meet the use, It needs to be combined in series and parallel to satisfy the surface conditions. In addition, because the internal resistance and capacity of each battery are different, the performance difference may lead to the reduction of the available capacity of the battery pack, thus shortening the service life. Consequently, it's necessary to use battery equalization technology to protect the battery pack. Yes, then it comes the third part, the classification and summary of battery equalization topology. The basic meaning and the essence of battery equalization are to use electronic technology to prevent the battery from being damaged during use and to ensure the safe operation. The battery equalization topology is generally divided into two types. One is energy consumption equalization, also known as passive equalization, which reduces voltage difference between batteries via energy dissipation. It can be divided into switch shunt resistance structure and fixed shunt resistance structure. However, passive equalization is not suitable for large batteries due to excessive heat and energy loss. Another equalization topology is non-energy consumption equalization, also known as active equalization. Compared with passive equalization, although the control is complicated and there are many elements, it has the advantages of high equalization current and low battery energy loss. It can be divided into capacitors, inductance, transformers, and converters equalization. Now I'm going to talk about mine. As you can see, this is a very basic flag-back converter. The flag-back converter essentially replaces the inductor between the MOS transistor and the diode of the buck-boost converter with a high-frequency switching transformer to achieve electrical isolation. And this is what I do. Based on an active equalization of a multi-input transformer, principle of active equalization of the transformer is analyzed and simulated. The transformer equalization topology realizes the changing and discharging state of the equalization unit through flyback conversion, thereby realizing the energy equalization between two adjacent battery modules. Yes, this is the circuit when both MOS transistors Q1 and Q2 are turned on. When VM1 is bigger than VM2, the modular M1 discharges M2 charges, and the current of the primary winding connected to Q1 rises and stores energy, and the current of the primary winding connected to Q2 rises in the opposite direction and releases energy. This is the circuit when both transistors Q1 and Q2 are cut off. When VM1 is bigger than VM2, the M2 charges and the transformer side winding current drops and the energy is released. The energy of M1 is transferred to M2 to achieve the equalization, and the arrows in the picture indicate the direction of current. Yes, and I then divided the simulation into two parts. In the first part, we don't have Q2, but in the second part, we have Q2. And during the simulation, we set the initial voltage and the capacitance differently to get the final result. Yes, you see, this is the this is the result of the Simulink and the scope. From the scope, we can get the figures like this. It shows the current, I1, I2, IS, and we can get the PWM figures. The Y is 50%. The I1 which is the module M1 current I1, and module M2, the current